Hello guys, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning I wish to all of you. So today I'm going to teach you differentiation method, which is Dunn method step by step. So I have published quite a lot of video regarding this matter, but I undergo a lot of questions. Some of them might be not clear, so today I'm going to clarify and explain again step by step what is Dunn method and how exactly to establish a good stepwise process so you actually can also provide the analysis to support your finding. Okay, we start with the introduction. So Dunn method normally is used to differentiate capacitive current and also diffusion control current. So this is okay, a lot of people already understand. And normally we are using cyclic voltammetry technique to use and to make sure that our material have the capacitive and also diffusion contribution. And cyclic voltammetry is also a powerful tool to measure the contribution of each what we call that each process, either is capacitive or diffusion control. And for especially for the Dunn method, we focus on the cyclic voltammetry that have a distinct properties. For example, the shape of the CV must have a redox peaks, because for Dunn method is specifically for your material that have the battery type properties. For example, if your material have EDLC or pseudo-capacitive, you can shift to the Transati method. Okay, back to the main equation that we're going to use throughout the process is IV, the current response at a specific voltage, equal to K1V. K is a constant, V is the scan rate, plus K2. K2 is constant, V power half. V power half is the scan rate power of half. And then we can develop the equation by divide by scan rate power half, so we get a new equation which is K1V half plus K2. Okay, these two equations can be used throughout the analysis of the Dunn method. Okay, I hope you understand. Okay, the next slide is slide number 3. It's about the step number 1. It's always start with the cyclic voltammetry. So you must run and collect your cyclic voltammetry at various scan rate, preferable 1 to 10 millivolt per second. You can also run until 5 millivolt per second, 6 millivolt per second, or you can try at high scan rate, but normally the battery type properties is dominant at low scan rate. But it doesn't hurt to try more. You can try like 10, 20, 30, 40, 50 until 100. Then you will see the deviation of the results. So you got your CV. Okay, here at the y-axis, either you can use current density or you want to use only current, it doesn't matter. But you must fix along the way until the end of the experiment. Okay, understand? Okay, next is we fix the voltage. At what voltage we want to measure the V value and the current response. Step 2 is a fix a voltage or a potential and read the current from the CV. A lot of question asking me how to read the current. How to read the current. Current is from the y-axis. You can use the origin, put your cursor here and see what is the current at the y-axis. It's as simple like that to observe the current response and read the current response. Potential. Okay, in terms of potential, a lot of questions arise. They said, so should we focus on the prominent redox peaks or prominent oxidation peaks or prominent reduction peaks? The potential doesn't matter. The only rule here is fix your potential. So here I fix at around 0.35 volt. So I read the current response at 0.35 volt for 1 millivolt per second, 2 millivolt per second, 3 millivolt per second, until 6 millivolt per second. So the only criteria you must follow here is the voltage must be fixed. You can go to 0.4, 0.5, it doesn't matter, but your potential must be inside your potential window. That's the important things to know. Okay. Okay, next is the next procedure is to apply the equation. So when we apply the equation, we plot the graph IV divided by scan rate power half. We got K1V power half plus K2. Okay, from this graph, we convert to simple mathematics, which is y equal to mx plus c. So from this procedure, because before this I choose until 6 potential windows, 6 scan rate, but here I only choose 4 because the two of the scan rate, the point is deviate so far, so it's quite difficult for me to get a straight line. So that's why the purpose to run at a higher scan rate. Don't limit to, even the minimum is only 3 scan rate or 4 scan rate, no need to go to the bare minimum. Okay, then the x-axis, you know the x-axis is the square root of the scan rate. The y-axis is the square root, what we call that. The y-axis is the square root of the current, so you can get the graph like this. And it is important at least the minimum value of point is 3 for you to able to plot the straight line. Okay, then from the procedure, you know that the slope is the K1 value. The y-intercept is the K2 value. So we can get K1 value and K2 value from this first graph. A lot of question about how to fit you can use from the origin. So from the origin analysis, click to analysis button, whichever origin file you have, version 12, version 20 and so on, even the version 8, also you can use analysis, fitting and also fit linear. You can get a linear like this and you can get a table. From the table, they will give you slope and also y-intercept. Okay, from that, what you're going to do, just use the value as K1 and K2. However, there is some difficulty in some experiment. You will get either both value is negative, either one is negative, one is positive. So here, what I can suggest you that you can actually ignore the negative value, focus on the positive value only. For example, if your slope is 0.98, y-intercept is negative 0.6, so just change negative 0.6 to 0.6, so make sure all the value is positive. Then we can calculate the percentage contribution. So a lot of questions also ask how to calculate the percentage of contribution. So now you already get your K1 value and K2 value. So just put the value on the equation, then you can get the percentage of contribution. Okay, for example, see here. Choose either one I capacitive of I diffusion. Don't be so what we call that ridiculous to calculate both of them. Okay, because I capacitive plus I diffusion equal to 100%. So if you calculate both, it's waste your time. Either choose either one. So let's say I choose I capacitive. To calculate I capacitive equal to I capacitive divided by I capacitive plus I diffusion times 100%. So for example, the K1 value that we got from the other slide is 0.98. And the scan rate is 1 millivolt per second. K2 value is 0.98. The scan rate power half is 1. You can use your calculator. Okay, then K1V is 0.98. K2V power half is 0.98. Then we can calculate capacitive contribution by insert the formula I capacitive divided by I capacitive plus I diffusion times 100. You got 59%. To get diffusion contribution, 100 minus 59, you got 41%. This is for first scan rate. You can go for second scan rate, third, and so on. So that is the formula to calculate the scan rate. Okay, I hope this clear for you. Okay, so in this case, it might be trouble if you include the negative value. So the total contribution will not equal to 100%. That's why I ask you to ignore the negative value. Okay, then when you already get the contribution, so you want to know at which area on your CV graph belong to the capacitive contribution and at which area belong to diffusion contribution. So based on the theory, in the inner side of the graph belong to the capacitive, at the outer side of the graph belong to the diffusion contribution. So based on this, you can roughly estimate how to plot your graph. Okay. Okay, this is a quite interesting, a lot of figures. So actually it's quite simple. Okay, step 6 is choose one scale rate and measure the oxidation and reduction current response at certain potential. So for example, your potential window is from 0 to 0.5. You can read the current response at the increment of 0.05. Or if you also can do at the increment of 0.01 or 0.02. In this case, I read the current response at the increment of 0.05. So from here, what I did is I read the normal reduction current and also oxidation current. This is the normal before the contribution ratio. Then I already calculate the percentage contribution, 15%, 85%, I put here. Okay, in your case, if you refer to the previous graph, it should be 59% and also 41%. Okay, this is the other example. Okay, it's almost the same. The only difference is the number. So here, what I'm going to show you here, I calculate both for the current response after at reduction and oxidation. But in your case, what you can do is you can just calculate one only. For example, is the diffusion, using the diffusion percentage to calculate the current response after and before. Don't calculate both. Don't calculate the percentage of diffusion and also percentage of what we call that percentage of capacitive. Diffusion and capacitive is the same. Don't calculate for diffusion limiting. Just calculate only one. So it will make you headache. Okay. So it's quite simple. For example, we already identify that the area inner area is belong to the capacitive. So it's very easy for you to calculate and to draw a graph for diffusion limiting for the redox process is the outer layer of the graph. For example, in this case, the percentage of diffusion is 0.15. Diffusion limiting is 0.85. So here, diffusions, you can either choose either diffusion or diffusion limiting. Just choose either one. So from here, for example, if I choose the percentage of diffusion 0.15, I just times the current that I read 0.10573 times with 0.15. So 0.1 at 15%, I know how much current it should be generated. Then the value should be at 0 volt should be only 15% of the current initial current. For example, at the same point 0.1 also should be 15% than the original current. So you got a dot that have lower amount of current, not 100% but only 15% of the current. So then you just have only dot. So you need to go to origin to plot your graph. So to get a very beautiful graph like this, you need to choose either B curve or S curve in the origin graph. So that one I will make another video for you, how to plot a very good graph using the origin. Okay, then you actually, it is possible to get graph like this. If you don't like to plot the graph like green and the black button, black line here, you can calculate both diffusion and also diffusion limiting. It doesn't matter. Both also can. So in order to visualize your finding, you can actually do whatever you want. You want to compare only the capacitive with the normal graph, or you can compare diffusion and diffusion limiting only. Okay, it's up to you, it doesn't matter. So then just calculate the B value just using the same current response, calculate the R square value. I think that's all. It's not so difficult. Okay, I hope the video can help you. So if you don't understand, it's of course you can ask directly on YouTube. So I will honestly answer with you and help in your experiment and also in your research. Okay, I think that's all. Thank you very much.